All right, today we're going to crack open the universe's ultimate instruction manual. We're talking about the fundamental, absolutely non-negotiable rules that govern every single bit of energy, from the biggest star all the way down to the phone you're holding in your hand.
You know, it all really starts with questions you might ask every day. Why does a hot cup of coffee on your desk always get cold? Why doesn't it ever just spontaneously get hotter? And for centuries, people have dreamed about it, but why is it completely impossible to build a machine that just runs forever on its own? Well, the answers to these questions, they reveal the deepest, most basic logic of how our entire cosmos works.
I think the best way to think about this is that the universe has a very strict rulebook when it comes to energy. And these aren't just suggestions or guidelines. These are the laws of thermodynamics, and absolutely nothing, and I mean nothing, is allowed to break them.
So, let's start with a rule that's so fundamental they actually went back and added it later, calling it Rule 0. This law is the foundation for how we even measure temperature. It's really all about things reaching a balance.
The big idea here is something called thermal equilibrium. It sounds fancy, but it's simple. When you put a cold object next to a hot one, say a cool spoon into a hot bowl of soup, energy moves from the soup to the spoon. It keeps doing that until they're both the exact same temperature. At that point, the energy transfer just stops. They've hit equilibrium.
And the logic of the zeroth law is it's beautifully simple. It just says, if a thermometer, let's call that C, tells you your coffee, A, is 60 degrees, and that same thermometer tells you the air in the room, B, is also 60 degrees, well, then you don't even need to check. The law guarantees that your coffee and the air are at the same temperature. This simple idea is what makes every single thermometer work.
And that idea builds right into rule number 1. If the zeroth law is about logic, then the first law is all about accounting. You can think of it as the law of conservation.
Now, this is one of the most famous lines in all of physics. What it means is that the total amount of energy in a closed system, and you can think of our whole universe as a closed system, is constant. It never goes up and it never goes down. It just gets moved around and changes its outfit.
So, here's a really crucial distinction to make. You have to understand what energy is versus what it does. Energy can exist in all these different forms, right? Like the internal energy shaking molecules around, the kinetic energy of something moving, or the potential energy stored up in an object. But it only gets transferred in two ways: as heat, which is that random flow of energy because of a temperature difference, or as work, which is an organized transfer of energy to, push or move something.
The money analogy here is just perfect. Imagine you have $100. You can exchange it for euros or for yen, but you still have the value of $100. You can't just magically create another 20 bucks out of thin air. The universe is like the ultimate accountant. Every single joule of energy is always accounted for.
Okay, this brings us to what many people think is the most profound and most important rule of them all, the second law. This one isn't just about accounting for energy, it's about direction. It tells us which way things are going to happen.
The second law pops up in our lives in two really big ways. First, it dictates that heat will always flow from something hotter to something colder. Always. That's why your coffee cools down. And second, it says that whenever you try to convert energy to do something useful, like in a car engine, you will always lose some of it as waste heat. Perfection is literally impossible.
Now, the concept that's driving all of this is called entropy. And I know that word can sound a bit complicated, but at its heart, it's just a measure of disorder or randomness. The second law basically states that in any isolated system, the total amount of entropy, the total disorder, will always increase over time. Or, at the very best, it'll stay the same. It never goes down.
Let's paint a picture. Imagine all the air molecules in the room you're in could be magically gathered into one tiny corner. That's a very organized, a very low entropy state. So, what happens next? Well, you know what happens. They're going to spread out, mix around until they're randomly scattered all over the room. That's a disordered, high entropy state. The universe always moves from order to disorder on its own. I mean, your bedroom doesn't spontaneously clean itself, right?
So there's your answer. The concentrated, ordered heat energy that was in your coffee naturally spreads out into the more disordered, cooler air of the room. And that increases the total entropy of the system. An egg is an ordered thing. When you break it, it becomes disordered. You'll never see the pieces just fly back together by themselves. This constant, one-way street towards disorder, that's what gives time its direction. It's the arrow of time.
So if these rules are so strict, how do we build anything at all? How does modern technology even exist? Well, that's where the genius of human engineering comes in.
And here's the crucial insight, the really clever part. We don't defy these laws. We can't. Instead, our most important machines, our greatest technologies, are designed to cleverly work within the limits of these unbreakable rules. The best example of this is the heat engine. This is basically any device, from a giant power plant to the engine in your car, that takes advantage of the natural flow of heat from a hot place to a cold place, and it siphons off a little bit of that energy along the way to do useful work for us.
Let's take a quick look. A car engine, right? It creates a hot source by burning fuel, it produces work to move the car, and then it dumps waste heat into the cool air. It follows the rule perfectly. Now, a refrigerator, that seems like it's breaking the rule, right? It's making a cold space even colder. But it's not. It uses work, it uses electricity to force heat to move from the cold inside to the warmer room outside. It's fighting against that natural flow, and it has to pay an energy price to do it. A heat pump, just the same idea, but in reverse. They all obey the law.
And that brings us all the way back to our second big question. This is exactly why perpetual motion machines are totally impossible. They fail for one of two reasons. A machine that creates its own energy out of nothing, that violates the first law. You can't do that. And a machine that runs forever by perfectly recycling its own energy with zero waste, that violates the second law, because every single process has to have some waste, some increase in entropy. The universe's rulebook just says, nope, can't be done.
So these laws, they don't just explain coffee and cars. They explain pretty much everything. But they also point to a final, pretty profound question. If the entire universe has to follow this one-way street from order to disorder, from useful concentrated energy to useless spread out heat, what happens at the very, very end of that road? What is the ultimate fate of a cosmos that's bound by the arrow of time?